Let me start with a quick question. How many of you have ever been affected by a data breach? Maybe your phone number is leaked or even your card details. Unfortunately, this is becoming the norm. According to the Australian Signals Directorate, there are over 87,000 cybercrime incidents reported just last year, and that's 1 in every 6 minutes. And the cost isn't small as well. Small businesses lose nearly 50,000 on average, while larger ones can lose over 60,000. At the core of these attacks are software vulnerabilities, the weaknesses in code that hackers exploit. And that's why in our research, we are focusing on compare and choosing the best way to detect software vulnerabilities.
In our research, we are going to compare two approaches, the traditional static analysis and the newer large language models. From past study, we know static code analysis is reliable and precise, but it can have scaling issues and often struggles with logic-heavy flaws. On the other hand side, LLMs can understand complex code semantics and can handle diverse inputs, but they can also be unstable and less transparent. So how do we choose? Although there are previous research done on this topic, there are still gaps remain. First, no standard tests for stability. Second, no consistent reporting of line-level precision. And third, no clear guidance on when to use static LLMs or a hybrid model. To cover these gaps, our approach is to evaluate both methods across two dimensions, performance and cost. Performance will be evaluated based on accuracy, efficiency, and coverage. For example, accuracy will be tested using precision, recall, and F1 score. And for cost, we'll consider deployment and operational costs and total cost of ownership. To combine these results, we use the CESI metric, the Cost Effectiveness Sustainability Index. It balances performance and cost into a single score so decision makers can easily see which tool gives the best overall value. Our tests will be run on well-known open source code bases like OWASP WebGold and the damn vulnerable web application. This is a 12-month project and each stage is shown in this table. Our plan also has built-in buffers to handle variations. For example, you can see we've kept the literature review running until month 7. This means we'll keep refining our experiments as new insights emerge and also leaves enough time to handle contingencies. This research will be significant as it provides a standardized way to compare vulnerability detection tools and helping organizations make evidence-based choices. At the international level, our framework helps government and industry strengthening their cyber resilience, cut costs, and protect sensitive personal data. This can lead to greater public trust. And internationally, this framework can encourage consistent global security standards and cooperation. And by including carbon emission into our evaluation, we also support greener, more sustainable deployments. Ultimately, this project provides a practical framework that makes vulnerability detection more secure, more affordable, and more sustainable.